Hello, I'm Ben. This is my second presentation on the second paper for Complex 5 to 921B Engineering Self-Adaptive Systems, Assignment 3. The title of this paper is Improving Self-Adaptive Systems, Conceptual Modeling by João, Pablo S. da Silva, Miguel, Ecar, Marcelo, Pimenta, Fabio, Natanael, Kepler, Gilleanes, Guedes, and Carlos Michel Betemps. Published in the Proceedings of the 33rd Annual ACM Symposium on Applied Computing in 2008. So, to describe what the problem is here, first we start off with an explanation of conceptual modeling. So, conceptual modeling is the act of creating models that describe problems a self-adaptive system may face and the situations where they arise. These are useful for requirements analysis as they aid in understanding the situations in which a problem might occur. The issue is that conceptual models are constructed by humans, often in an ad hoc process, and thus are dependent on human expertise and are prone to errors or oversights. This is not a good software engineering practice, as it can lead to failings such as model misinterpretation, overcomplexity, lack of separation of concerns, and cohesion and coupling problems. Why is it still a problem? Well, as stated previously, conceptual modeling is primarily performed by humans, and this leads to all the problems described earlier. An autonomous method of creating, refining, and consolidating conceptual models solves all of these problems. For related work, the authors of this paper identified three main concerns related works addressed. First, enhancing the adaptation aspect of the self-adaptive system, which addresses the outcome of poor conceptual modeling by adapting better to the unforeseen problems occurring. Second is by better modeling of the context requirements, which are requirements that constrain the system's interaction with its environment. This addresses the issue by more strictly regulating the primary area unforeseen problems come from. Lastly is dealing with uncertainty. This mainly involved the relaxation of requirements to encapsulate more area and thus reduce the area uncertainty can come from. So the main goal of this paper is to reduce the quality risks in self-adaptive systems conceptual modeling. And to do this, the authors proposed a methodology for creating better conceptual models made up of two parts: a meta model, such as the one shown here, and a modeling process. This process comprises 4 steps, beginning with a requirement specification as input and ending with a conceptual model as output. The first step is to model actors. This is done by reading the specification and identifying the actors, which are things performing some actions, and creating classes for them. Next, actions are modeled. This is done by reading after each actor to see what actions they perform, creating classes for them, and then linking them to their respective actors. Third is conditioners. Conditioners are restraints applied to actors and can be obtained by reading after actions in the specification to find any clauses that restrict how the action may be taken. Then, classes are made for them, and they're linked to their actions. Lastly, we have information. Information is modeled as a relationship between a monitor and an environment and is tied to actions to inform their decisions. So let's briefly look at an example. So here's a specification written in Relax, which we use in input. Relax is a specification language, an informal specification language, we should say. The capitalized words have special names, so modal operators like shall and may or, temporal operators like eventually, before, until, or as early or as late as possible, and ordinal operators like as many or as few as possible. The paper defines actors, conditioners, and information in terms of these operators within the specification. Firstly, we identify actors as things before modal operators. So here the modal operator is shall, and the actor we identify before the word shall is the smart car. So we create an actor called smart car. Secondly, actions are defined as things between modal operators and temporal or ordinal operators. So here again, we've only got one modal operator, and that's shall. And then straight after that, we have as few as possible, which is an ordinal operator. So between those two, we have the word plan. So our action is going to be to plan or planning. Next, conditioners. Those are written after temporal or ordinal operators. And there's two here because there's two of those operators. There's as few as possible, which we identified earlier as an ordinal operator. And there's also after, which is a temporal operator. And we identify, therefore, two conditions, which are refuelings and trip starts. Right? And the relationship here is, of course, after and as few as possible, lining up with those operators from the specification. Lastly, to model the information, we first need to find environments and monitors. And in Relax, environments identified on that list there under ENV. So there's two, there's smart car and roadmap. And monitors are on the MON list there. So we've got two, service sensor and consumption sensor. Then what we do is we link the monitors to the environments according to that third line there, which is rel, or relations. And it tells us the service sensor monitors roadmaps and the consumption sensor monitors smart cars. So now we can create those classes and link them all together to create our monitor, environment, and information classes there. How is this better than what's already being done? Well, introducing a standardized process for developing conceptual models brings a level of consistency to them which isn't currently seen with current ad hoc methods. Additionally, the output format being a UML diagram in primarily plain English increases its usefulness in presenting to stakeholders or other people who lack technical knowledge. The systematic approach to creating a conceptual model greatly reduces the chances of oversight on behalf of the engineer, particularly because the full requirement specification is used in generating it. To test the efficacy of their process, the authors designed an experiment where two groups were tasked with designing some conceptual models based on the same specification. Each group was also given the same material to prepare with, including information on Relax requirement specifications and UML for conceptual modeling. The experimental group were additionally given the proposed modeling approach described in the paper, while the control group received some off-topic text. The authors proposed two hypotheses. The null hypothesis being that F-scores, a measurement of performance for both groups, would be equal, and the alternative hypothesis that the F-scores would be non-equal. You can see on the second diagram there on the right, their definition of F-score. The conclusion of this experiment was that the experimental group significantly, with a p-value of 0.0003, outperformed the control group. One note that the authors made is that these groups were formed from students who, while having studied the related field of requirements engineering and being from a range of years of study, are not real experts and have little practical experience. Thus, the results can't be generalized to other populations. So, my critique, while a standardized systematic approach to conceptual modeling is certainly advantageous over generally doing such tasks ad hoc, there are surely many requirements engineers or companies in general who have developed a personal or internal method of creating good conceptual models. And since the evaluation the authors performed doesn't take such a population into account, it's unclear whether this method outperforms what experienced people are already doing. It must be asked, however, if the intention of the authors was to create a new industry standard way of doing conceptual modeling, or merely providing an easy-to-learn framework for the newer engineers to adopt and use themselves, without relying on learning from an experienced senior engineer or from developing their own practices. And this isn't made clear in the paper. Thank you.